Welcome to MEI Mechanics. We're on the topic of forces and moments, and this is video 1.1, friction. Now, friction can occur when objects are in contact with each other. So if you have say a plane, might be horizontal, it might be on the slope, and we have an object which is in contact with that plane, then there'll be forces on the object from the plane, and of course forces on the plane from the object. There'll also be the weight of the object, but the two forces that we're going to be thinking about are the normal reaction force, often given the symbol R, and that acts always perpendicular to the plane, so it makes a right angle with the plane. And then there could also be a frictional force, and depending on what other forces are acting on the object, which way the object wants to move, the friction could be acting in either direction. So it could, for example, be acting that way up the plane, but it was always parallel to the surface. Okay, so the normal reaction force R is perpendicular to the surface, and the frictional force F is parallel to the surface. And the total contact force is the sum of these two vector components. So let's think about what happens in more detail when we're dealing with friction. So if the object is sitting on a rough surface with a force P being applied one way, so that's a push or a pull, someone's trying to move that object along the plane, then if it's a rough surface, then if the force is small enough, then nothing will happen. So if we're in this case here, well, there'll always be the weight acting downwards and a normal reaction acting upwards, and the friction will be equal and opposite to P, so that the object doesn't move. So these two forces P and F cancel each other out completely. Now as P grows, as P gets bigger, the friction will have to get bigger as well in order to compensate for it. So if it's just on the point of sliding, then again that frictional force F will be equal and opposite to P. And then if P goes beyond that, so if P increases further, then the object will start to slide. So in this case, again we've got F acting in that direction. But in these two cases, we had F, in terms of its size, equal to P. But in this case here, then P is greater than F. So that there is an overall force acting to the right there, and the object starts to slide. Now there's a relationship then between that maximum friction when the object is just on the point of sliding, which is something called limiting equilibrium, and the normal reaction force R, and they're related through this constant mu, which is called the coefficient of friction. So that will depend on the materials that this surface is made from and the object is made from. So that will be different in different situations, that number. But that gives you the maximum friction that you can have. So it's proportional to the normal reaction force through this constant mu. And so if the object is not sliding, then F will be less than mu r. If the object is on the point of sliding, or if it is sliding, F will be equal to mu r. So this coefficient of friction, as we said, depends on the materials that the object is made from and the surface is made from, and so in reality you'd have to determine that by doing an experiment. There are some typical values. So if you had skis on ice, well obviously that they're designed so that they slide along the ice, so that would be very low value, for example maybe 0.01 to 0.03. Notice that this coefficient of friction is dimensionless, so there are no units. a book on a wooden table, that might be a higher value, say between 0.3 and 0.6. And then tyres on the road, well, they're designed to grip the road and provide a lot of traction on the road, and that is actually a form of friction. So that could be, say, between 0.6 and 1.3. So it is possible for the coefficient of friction to be greater than 1. That might be surprising, perhaps, but it is actually possible. So it can be greater than 1. So let's have a look at an example now. So we've got a box, mass 15 kilograms. It's resting on a rough horizontal surface. And notice that we've met examples with a smooth surface as well. If we're told it's smooth, then we're told that means that there's zero friction. If it's rough, then it means that there is friction. And we have a force of P being applied to the box to the right. So that means that there will be friction acting to the left. And it says that when P equals 100 newtons, then the box will be in limiting equilibrium. Okay, and that should be enough information for us to work out the coefficient of friction, mu. So let's look at this force diagram. So we've got this weight, which is the mass 15 times g, and then there'll be a normal reaction force R. So thinking about vertical components, resolving vertically, this thing's not going to move up or down, so we know that R minus 15g, that must equal 0, because we have no vertical acceleration. And that means that R itself is equal to 15g. And then if we look horizontally, we have P acting that way, and we have F acting to the left. But we're told that the box is in limiting equilibrium, and when it's in limiting equilibrium, it means that this F has its maximum value. So I can actually label this as F max, because we're told it's in limiting equilibrium. So we have P minus F max equals 0. And so because it's in limiting equilibrium, that F max, that friction, is its maximum value F max, which is mu R. And so that means that P, which is 100, minus mu times R, which is 15g, equals 0. So we can then work out what mu is using g equal to 9.8, and that comes out as mu equals 0.680, or let's say 0.68. Keep two significant figures there. So part B of this example then asks us to find the acceleration of the box when P equals 130. Now again, let's draw a force diagram. In particular, we're going to look at the horizontal components here. So P is 130 newtons now, and we know that that maximum friction was just 100 newtons. So that friction, it can't exceed its maximum value. So if P is greater than that maximum value, the frictional force will just be equal to its maximum value of 100 newtons. Okay, so we have 130 minus 100. And this is no longer equal to 0 because this thing is accelerating. So when it's accelerating, that force, of course, that overall total force, will be MA. And we know that the mass is 15, so that's equal to 15A. So we have 30 equals 15A, which means that A is 30 divided by 15, so A is 2 meters per second squared. Now here's a second example, and this time the situation is a little bit more complicated because we have an object which is sitting on a plane. Now it's almost always sensible in a case like this to resolve the forces not horizontally and vertically now, but parallel and perpendicular to the plane. So we set up the diagram like this, and we make sure that we keep the weight of the object acting vertically downwards, and so that will make an angle equal to this same angle here, this angle alpha, with the normal to the plane. And so we have three forces acting. We've got the normal reaction force, which is normal to the plane. We've got the weight, and then we'll have the frictional force. And it's that frictional force which is stopping the box from sliding down the plane, so it must be acting up the plane. And we're told again here that the box is on the point of sliding, so we know that this frictional force will actually have its maximum value at that point. Okay, so let's label that F, that's R, that's the weight, which is 15g. And let's think about components normal to the plane firstly. And so we have R acting that way, and then we've got a component of the weight acting downwards, so we need to resolve this force like this, and we can see that the component which is acting to oppose R is adjacent to this angle, so it will be given by a cosine. So we have R minus 15g cos alpha will equal 0 because it's an equilibrium, and then that means that R itself will be equal to 15g cos alpha. And then if we look parallel to the plane, we have F minus the horizontal component of this weight, so that's 15g sine alpha. That will equal 0. And because we're in limiting equilibrium, that F will have its maximum value, F max, which is mu r. So I can say that mu r minus 15g sine alpha equals 0. Now we need to do a bit of algebra here, so we can combine these two equations together. I know that r is 15g cos alpha, so I can replace this r here with 15g cos alpha. So I have mu times 15g cos alpha, and then if I take this over to the right, that will be equal to 15g sine alpha. Now a couple of things to notice then here. Firstly, I've got 15g on both sides. I can cancel that, and then if I want to get mu, then I'm going to need to divide by cos alpha. So I will have mu is equal to sine alpha over cos alpha, which of course is tan alpha. Right, now we're told of course that mu is 0.68, so that means that alpha will be the inverse tan of mu, which is 0.68. So alpha itself is 34.2 degrees. So that concludes video 1.1 on friction. The next video, 1.2, will be on moments and couples.